Hello, settle in gently and let your attention drift toward a very old Earth. Imagine looking down from space at a planet that is familiar only in the broadest sense. It is round. It turns in sunlight. It carries oceans and rock, but there are no forests, no animals, no green continents, and no voices rising from the land. The world is alive, but almost all of that life is hidden, working quietly in water, smaller than sight, patient enough to change the air. If you enjoy calm journeys through Earth history, you can like this video and subscribe, and stay with me for more slow travels through deep time. Now, let the room become quiet. Let your breathing settle into an easy rhythm. The day can loosen its grip. The light can soften. We are going far back, not by thousands of years or millions of years, but by billions. We are entering the Proterozoic Eon, a stretch of time so long that the mind has to move slowly just to stand near it. The Proterozoic began about 2.5 billion years ago, and it lasted until about 541 million years ago. That is almost 2 billion years of Earth history, a long, quiet corridor between the young, violent planet and the later world of visible animals. If all of Earth history were a long evening, with the first rocks appearing near dusk, and human beings arriving almost at midnight, the Proterozoic would be the calm middle hours, when the room is dim, the fire is low, and most of the important work is happening out of view. It is strange to imagine an eon so large and so easy to overlook. Dinosaurs get more attention. Naturally. They had teeth, tails, horns, and the good sense to look impressive in museum halls. The Proterozoic had no dinosaurs, no flowers, no birds, no grass, not even a fish moving through the water. It did not offer much that a visitor could point to and say, "There it is." Its story was written in chemistry, in stone, in air, in cells too small to see. But quiet is not the same as empty. The Proterozoic was one of the most important chapters in the making of the planet we know. During this immense span, continents grew stronger. Oceans changed their chemistry. The atmosphere began to receive oxygen. The sky slowly moved toward the colors we know. Cells became more complex. Life learned how to cooperate. And far later in the eon, soft bodies would begin to appear on the sea floor like faint impressions in a dream. At the beginning of the Proterozoic, Earth was already ancient. It had survived its early formation, heavy bombardments, volcanic unrest, and the long cooling that allowed oceans to settle across its surface. But it was still not a comfortable world. The air would have been unbreathable to us. The sunlight was dimmer than today. The moon was closer. The days were shorter. The continents were not the familiar shapes of Africa, Asia, Australia, or the Americas. They were low, body, shifting land masses, scattered across a planet, still learning how to hold itself together. If you were somehow standing on that land, protected from the air and radiation, you would not hear birds. You would not hear insects. There would be no rustle of leaves, no scent of soil after rain, no roots gripping the ground. The surface would be rock, dust, volcanic plain, and shallow water. Wind would move across the land without meeting grass. Rain would fall on stone without feeding forests. Rivers existed, but they carried sediment through landscapes with no plants to slow them down. The world had edges, but not softness. The continents themselves were forming from ancient cratons, the oldest stable cores of land. These cratons are still with us today, buried beneath parts of North America, Africa, Australia, and other continents. They are geological elders, thick and resistant, survivors from a time when the surface was being remade again and again. During the Proterozoic, these old cores collided, separated, thickened, and became the foundations of future continents. Nothing about it was fast. A continent does not hurry. It drifts with the patience of stone. Below the crust, the mantle moved slowly, carrying heat from Earth's interior. Convection currents pulled and pushed the plates above them. Land masses shifted across the globe, sometimes coming together into early supercontinents, sometimes breaking apart again. Names like Columbia or Nuna belong to these ancient arrangements. Their exact shapes are debated because time has folded, buried, and erased so much evidence. Still, the rocks keep fragments of the memory, matching mineral belts, ancient mountain roots, and magnetic clues suggest that pieces of today's continents once touched in ways that now feel impossible. Above those rocks, the sky was not yet our sky. The sun shone with less energy than it does now. Perhaps around 85% of its modern brightness in the early part of this story. That dimmer light should have made Earth colder, but greenhouse gases helped hold warmth close. Methane, carbon dioxide, nitrogen, water vapor, and volcanic gases shaped the air. There was little to no oxygen at first, and no protective ozone layer. Ultraviolet radiation poured down from space, harsh and unfiltered. For fragile life, the land surface was not inviting. Water was safer. Oceans acted like a shield, absorbing radiation, smoothing temperature changes, giving life a place to remain hidden while it experimented. And those oceans were not the clear blue waters we might imagine. They were darker, murkier, and chemically unfamiliar. Much of the ocean lacked free oxygen. Dissolved iron drifted through the water. In some places, the sea may have looked greenish, reddish, or brown, depending on local chemistry and light. It was water, yes, but not the water of a coral reef, not the bright shallows of a holiday postcard. More like a vast mineral broth, quiet, heavy, and alive with invisible work. Life had already existed for a long time. Bacteria and archaea had found ways to survive in heat, salt, darkness, acidity, and mineral-rich environments. They lived near vents, in sediments, in shallow pools, in places without oxygen and often without sunlight. They were not glamorous, but they were very good at being alive. They absorbed chemicals, released gases, used energy in ways that seem strange to us now. and built communities that reshaped their surroundings, one molecule at a time. You might notice how small the story feels at first. No animals crossing a plain, no wings in the air, no eyes watching the horizon, just cells, tiny living systems in the water and mud. But those cells were the main characters. They were not waiting for something more important to arrive. They were the world. They set the pace. And for a long time, the pace was slow. In shallow seas, microbial mats began to spread across surfaces where sunlight could reach. They were thin, layered communities, soft coatings of life clinging to sediment and rock. Some layers used light. Others lived beneath, consuming waste products and recycling nutrients. Over time, these communities could trap sediment and build structures that became stromatolites, domed or layered formations that still survive as fossils and, in a few special places, as living examples today. A stromatolite grows with remarkable patience, layer after layer, grain after grain, film after film. It does not bloom like a flower or rise like a tree. It builds by repetition. It is almost funny, in a gentle way, that some of Earth's earliest great builders looked like lumpy, wet rocks. Not exactly a glamorous construction crew, but extremely effective. For hundreds of millions of years, such microbial worlds spread across shallow environments, creating living landscapes long before any animal would crawl, swim, or blink. This is the central mood of the early Proterozoic. Hidden activity, slow transformation, a planet that appears quiet from a distance, but is changing from within. Rocks are forming, continents are assembling, oceans are holding dissolved iron, microbes are adjusting the chemistry of air and water. The future is not visible yet, but the ingredients are gathering. Some of those ingredients were elements released by geology. Weathering and volcanic activity made nutrients available, including phosphorus and molybdenum, elements that would later matter deeply to living cells. No mineral knew it would someday help build DNA or power enzymes. Stone does not plan, but life uses what the planet offers. And over deep time, small chemical opportunities become enormous biological consequences. In the early seas, one group of microbes began to do something that would change everything. Cyanobacteria learned to use sunlight in a powerful way. They took in carbon dioxide and water, captured energy from light, and released oxygen as a byproduct. They were not trying to prepare the world for animals. They were not thinking ahead, because thinking did not exist yet. They were simply living, following chemistry that worked. At first, the oxygen they released did not fill the atmosphere. It vanished almost as soon as it appeared. It reacted with iron, sulfur, volcanic gases, and organic matter. The planet absorbed it like dry ground drinking the first rain. But the microbes kept going. Day after day, teed after teed, generation after generation. Tiny cells in shallow water released tiny amounts of oxygen. It is easy to miss the scale of that. A bubble here, a reaction there, a film of cells under sunlight. Nothing dramatic. Nothing that would make a sound Yet this was the beginning of a planetary change. The oceans would slowly rust. The air would slowly shift. Many old forms of life would be forced into retreat. Other forms would adapt. And one day, far ahead, the oxygen that began as waste would become the breath of animals, forests, and us. For now, the planet remains quiet. The young sun glows over low continents. The moon hangs larger in the sky. Wind crosses bare stone. Oceans move under a strange atmosphere. And beneath the surface, life continues its small, steady work, preparing Earth for changes no eye has yet evolved to see. The camera drifts downward now, through the dim young sky, through pale clouds and over the empty edges of land, until it reaches the ancient sea. From above, the ocean might look calm, a dark skin stretched across the planet. But beneath the surface, it is not the ocean we know. It is heavier with minerals, quiet in its movement, and almost entirely without oxygen. These were anoxic oceans. That word simply means there was no free oxygen dissolved in the water. To us, oxygen feels like a sign of life, because our bodies depend on it so deeply. But in the early Proterozoic, oxygen was not yet a friendly presence. Most life did not need it. Much of life could not tolerate it. The sea was ruled by older chemical pathways, by microbes that used sulfur, methane, iron, nitrogen, and other substances in ways that feel almost alien when compared with modern animals and plants. If you were floating there in a protected vessel, looking through the water, you might not see much at first. No fish would turn in the distance. No shells would scatter across the seafloor. No kelp forests would sway. No jellyfish would pulse gently through clear blue light. The water might be greenish in one basin, reddish or brown in another, cloudy with dissolved iron and other minerals. The light would enter, but not far. The world below would feel quiet, muted, and strangely full. The fullness would be chemical. It would be microbial. It would be happening at a scale your eyes could not follow. Microbial life found many ways to exist in this water. Some organisms lived near hydrothermal vents, where hot, mineral-rich fluids rose from the seafloor. Imagine black water in the deep, not black from dirt, but from the absence of sunlight and the presence of minerals. Heat shimmered into cold water. Chemical clouds drifted outward. There, microbes could feed not on sunlight, but on chemical energy. They did not need a sunrise. They needed a gradient, a difference between one chemical state and another. Other microbes lived in shallow areas, where light reached the seafloor and small communities spread across sediment. These microbial mats were among the most important ecosystems of their time. They were not dramatic to look at. From the outside, a mat might seem like a thin greenish or brownish film, soft, slippery, quiet. A modern beachgoer might step over it without much admiration, which is a little rude, considering it may be related to the kind of life that helped make the air breathable. But inside that thin layer was a whole world. The upper surface met the sunlight. There, photosynthetic microbes captured energy. Beneath them, other organisms used the waste products from above. Still deeper, In low oxygen or oxygen-free layers, different microbes broke down organic matter, processed sulfur, released methane, and recycled nutrients. A few centimeters of mat could contain a complete chemical city, layered by light, depth, and need. This is one of the gentle wonders of the Proterozoic. Life did not need forests or coral reefs to become organized. It organized itself in slime, mud, and mineral films. It made neighborhoods without streets. It created recycling without bins. It had energy zones, waste pathways, and chemical cooperation long before any creature had a nervous system or a face. Over time, some microbial mats trapped sediment. Tiny grains of sand and silt settled onto their sticky surfaces. The microbes grew upward through the sediment, then trapped more. Layer after layer built slowly. Minerals precipitated. The surface hardened. These structures became stromatolites, rounded, domed, flat, or column-like, depending on conditions. They were made by life and geology together. Biology held the sediment. Chemistry turned it towards stone. Picture a broad, shallow sea, calm under a dimmer sun. Across the seafloor, low domes rise from the sediment, some small as bowls, others wider, arranged like a quiet garden of stone and film. Thin sheets of microbes cover them, shining faintly when the light catches the surface. A ripple moves over them. A tide returns. A thin layer of sediment settles. Time passes. The mat grows again. Nothing hurries. That is important. The Proterozoic does not unfold at the speed of animals. It unfolds at the speed of chemistry, sedimentation, mutation, and continental drift. A microbial mat can be active every day, yet the structure it builds may take thousands of years to become visible. The Eon asks us to slow down until small things feel large. In deeper waters, away from sunlight, other microbial worlds continued their work. Archaea and bacteria lived within sediments, in low energy conditions, sometimes dividing rarely, surviving in narrow chemical zones. Methanosians produced methane, a gas that would rise into water and atmosphere. Methane was important because the young sun was dimmer. Without enough greenhouse warming, Earth might have frozen more easily. Methane helped trap heat, holding warmth like a thin, invisible blanket around the planet. But that blanket was delicate. It depended on chemistry, volcanism, ocean conditions, and microbial activity. If oxygen later increased, methane would be broken down. That would cool the planet. In this way, the smallest cells could influence the climate of the whole world. Not by intention, not by plan, just by living. In the shallow waters, cyanobacteria became especially important. They were not the first life, and not the only photosynthetic organisms, but they developed a powerful form of photosynthesis. They used sunlight to split water and build sugars from carbon dioxide. Oxygen came out as waste. At first, that waste was swallowed by the environment. The iron-rich ocean absorbed it. Volcanic gases reacted with it. Organic matter consumed it. The oxygen disappeared almost as quickly as it was made. Still, the process continued. Imagine the top layer of a microbial mat at sunrise. Light moves across shallow water. The cells begin their quiet chemistry. There is no sound, no visible effort, no dramatic sign. But within those tiny cells, water molecules are being split. Energy is being captured. Oxygen is being released. A few bubbles may form and drift upward. Most of the oxygen stays dissolved, moving only a short distance before finding something reactive. Iron is waiting in the water. When oxygen meets dissolved iron, the iron oxidizes. In simple language, it rusts. Not like an old hinge or a forgotten garden tool, but as tiny particles forming in the water and falling slowly toward the seafloor. Over long spans, these particles settle into layers. Later, silica-rich layers form too. The result is banded iron formation, rock with alternating bands that can still be seen today in places like Australia, Canada, South Africa, and Brazil. These rocks are beautiful in a patient way. Red, dark, silver, gray, sometimes folded by later tectonic forces. They are mined today for iron ore, but they are also pages from an ancient ocean. Each band speaks of chemistry changing, oxygen appearing, iron leaving the water, life nudging the planet toward a new state. A banded iron formation is not only a rock, it is a memory of the sea rusting. The rusting did not happen everywhere at once. Some shallow areas became oxygenated locally, while deep waters remained anoxic. Scientists describe parts of the Proterozoic Ocean as stratified, with different chemical layers stacked through depth. Near the surface, oxygen might appear. Lower down, oxygen would vanish. In some mid-depth waters, hydrogen sulfide may have accumulated, creating conditions that would be toxic to most modern life, but suitable for certain microbes. So the ocean was not one simple environment. It was a layered world. Light above, darkness below. Oxygen in pockets, none in others. Iron in some basins, sulfur in others. Methane rising, minerals falling, microbes adjusting to each narrow zone. If modern ecosystems are like forests with many visible species, these oceans were like quiet chemical tapestries, woven in gradients that only instruments and rocks can now reveal. For many microbes, oxygen was dangerous. It could damage proteins and DNA. It created oxidative stress. Life that had evolved in a world without oxygen suddenly had to cope with a reactive gas entering its environment. Some lineages likely disappeared. Others retreated into sediments, vents, and deeper waters where oxygen could not reach. Others evolved defenses, enzymes and chemical pathways that allowed them to survive exposure. A few would eventually learn to use oxygen itself as an energy advantage. There is no need to make this frightening. It was not a sudden apocalypse with noise and fire. It was a slow reorganization of the microbial world. A quiet crisis measured over millions of years. The kind of change that would be invisible day by day, but immense when read in stone. As the iron sinks filled and reactive gases were consumed, oxygen began to last longer. It moved from local waters into the atmosphere. At first only a trace, then a little more. The air began to change. Methane began to decline as oxygen reacted with it. That meant less greenhouse warming. Earth became more vulnerable to cooling. The same microbes that helped build oxygen also helped set the stage for ancient ice ages. The sea kept its slow record. Rusty sediments fell. Microbial mats grew. Deep vents exhaled mineral-rich fluids. The sky above the water shifted by degrees too small for any single moment to notice. And still there were no animals, no eyes, no observers. Only life and planet, exchanging gases in the dark patience of deep time. By the end of this stage, Earth has not become modern. It is still strange, still microbial, still mostly silent. But a direction has opened. Oxygen has found a place in the world. The oceans have begun to lose their dissolved iron. The atmosphere has started to shift away from its earlier haze. And the tiny organisms in the shallows, unaware of futures they will never see, continue their work beneath sunlight. Now the camera rises again, gently, from the layered mats and rusting seafloor. It moves upward through dark water, past drifting mineral particles, toward the surface. Above the waves, the air is beginning to change. Methane haze will thin. Light will sharpen. Ozone will gather high above. And slowly, over ages beyond counting, the sky itself will begin to look a little more like home. The tiny bubbles rising from those ancient mats did not look important. If there had been eyes to watch them, those eyes might have missed them completely. A shimmer in shallow water, a faint disturbance on the surface of a living film, a little oxygen released into a sea that was still rich with iron and old chemistry. Nothing hurried. Nothing announced itself. Yet this was one of the great turning points in the history of Earth. Cyanobacteria were small, but they were not minor. They were simple compared with later cells, and yet they had discovered a powerful way to live. They used sunlight, carbon dioxide, and water, and from that quiet exchange they made sugars. Oxygen was left behind as waste. That word, waste, is worth holding gently for a moment. The gas that fills your lungs now began. In this ancient chapter, as something living cells were simply trying to get rid of. It is strange to imagine. Every calm breath you take tonight depends on the leftovers of microbes that floated in shallow seas billions of years ago. They had no intention of helping future forests, animals, or sleeping documentary listeners. They were not planning anything. They were only surviving, following the chemistry that gave them an advantage. Evolution often works like that. No grand plan, just small changes that happen to work, repeated until the planet itself is different. At first, oxygen could not remain free for long. The world had too many things ready to react with it. Dissolved iron filled the oceans. Volcanic gases entered the air. Organic matter lay in sediments. Every new bit of oxygen met some waiting chemical partner and vanished into reaction. The system absorbed it like dry ground drinking the first rain. For a very long time, the atmosphere barely noticed, but the cyanobacteria continued. Day after day, teed after teed, season after season, although seasons then were not quite like ours. Sunlight fell through shallow water. Microbial mats warmed. Cells performed the same reactions again and again. Oxygen spread a little farther. Iron rusted a little more. The ancient ocean slowly changed color and chemistry. Imagine looking down into a shallow Proterozoic sea. The water is not clear blue. It is greenish in one place, brownish in another, perhaps reddish where iron and sediment gather. Light breaks on low waves, then enters the water in soft beams. Beneath it, microbial mats cover the seafloor like uneven velvet, slick and alive. From their surface, oxygen moves outward. It meets dissolved iron, and the iron changes. Tiny particles form, too small to see one by one, and begin sinking. For millions upon millions of years, those particles settled on the seafloor. They formed layers. Some layers were rich in iron, others were richer in silica. Over time, pressure and heat turned them into rock. Today we call them banded iron formations. They are found on several continents, in places now far from one another, because the old seafloors have been lifted, folded, split, and carried by the restless crust. These rocks can be red, dark, gray, metallic, and striped like a slow memory. They are useful to industry, but they are more than ore. They are records of a planet changing its breath. Each band tells of iron leaving the ocean. Each layer says, oxygen was here, then less here, then here again. A stone like that is almost a sleep diary for Earth, written not in words, but in rust. The rusting of the seas was not one clean event. It came in pulses. Oxygen production rose and fell with microbial activity, nutrient availability, ocean circulation, and geological change. Sometimes oxygen remained local, near the mats that produced it. Sometimes it spread across larger regions. The deep ocean often stayed anoxic for much longer than the surface. So Earth did not become oxygen-rich all at once. It learned slowly, unevenly, like someone adjusting to a new rhythm of breathing. For many ancient organisms, that new rhythm was difficult. The microbes that had evolved in oxygen-free worlds were not prepared for a reactive gas moving into their habitats. Oxygen could damage enzymes, interfere with metabolism, and break delicate molecular systems. To them, it was not refreshing. It was stressful, sometimes deadly. The Great Oxygenation Event was not a gift to everyone. For much of the old microbial world, it was a slow crisis. Still, life did what life often does. It retreated, adapted, and changed. Some organisms moved deeper into sediments, away from the oxygenated shallows. Some remained near hydrothermal vents or in chemical pockets where the old conditions persisted. Others evolved defenses against oxygen, molecular tools that could neutralize its harmful byproducts. And eventually, Some lineages learned to use oxygen itself. That was a profound shift. Oxygen-based respiration releases far more energy than many older metabolic pathways. At first, oxygen was a problem. Later, it became an opportunity. This is one of the quiet patterns of deep time. A disturbance becomes a resource. A waste product becomes a doorway. A danger becomes the foundation for future complexity. The rocks preserve part of this transition. In some places, banded iron formations decline as dissolved iron in the oceans becomes depleted. Oxygen has reacted with much of what it could easily find. With the great iron sinks filling up, oxygen begins to linger in surface waters, then leak into the air. The atmosphere, once almost without free oxygen, starts to carry it in measurable amounts. This did not happen overnight. The phrase great oxygenation event can sound neat and tidy, like a single entry in a timeline. But the real change unfolded over tens of millions of years, perhaps longer, with reversals and pauses. If you could watch it in fast motion, you might see the oceans clearing gradually, rust falling to the floor, gases shifting, sky haze thinning, ice beginning to gather in future cold periods. But in ordinary time, in the time of a wave or a cell division, nothing would seem dramatic. The methane in the atmosphere mattered too. Methane had helped keep Earth warm beneath the dim young sun. It is a strong greenhouse gas, very good at trapping heat. But oxygen reacts with methane and breaks it down. As oxygen rose, methane levels likely fell. With less methane, the planet lost some of its insulating blanket. The air became less able to hold warmth. The cooling that followed may have helped set the stage for some of Earth's earliest major glaciations. So the work of cyanobacteria reached far beyond the microbial mat. It altered the ocean. It changed the chemistry of air. It affected climate. It created new pressures on life. It helped form minerals that would one day be mined from ancient rock. All of this came from cells so small they would vanish on the tip of a finger. You might think of a shallow lagoon under a pale sun. The tide is low. The microbial surface glistens. There is no sound except water moving gently over sediment, although, of course, there are no ears to hear it. A thin film of life captures light. Oxygen rises. Iron falls. The planet changes a little. Then another day. Then another. Then 1,000,000 years. Then 100 million. This is the patience of the Proterozoic. The cyanobacteria themselves were not alone. Their mats were communities. Beneath the oxygen-producing top layers, other microbes consumed organic matter and used different chemistry. Some processed sulfur. Some fixed nitrogen. Some lived where oxygen faded into anoxia. Together, they created vertical worlds, only millimeters or centimeters thick, but rich with interactions. The upper layer breathed light. The lower layers worked in shadow. Waste from one group became food for another. The mat was not a simple coating. It was a living system. Stromatolites built by such communities became common in many shallow environments. They grew as mats trapped sediment and minerals accumulated. The shapes varied with water depth, wave energy, sediment supply, and microbial behavior. Some were flat, some were domed, some rose like small columns. They were not fast growers, but they were persistent. Persistence is one of the most underrated powers in Earth history. Modern stromatolites still exist in a few places, such as hypersaline lagoons and isolated coastal settings where grazing animals are limited. They are like living windows into a world before mouths became common. In the Proterozoic, with no animals to scrape them away, microbial mats could spread widely. They carpeted shallow seas and quietly engineered local environments. They stabilized sediment, changed water chemistry, and created habitats for other microbes. As oxygen increased in some surface waters, the deeper ocean remained chemically older. Scientists describe these waters as stratified, layered by oxygen, sulfur, iron, and other conditions. In some intervals, mid-depth waters may have become sulfidic, rich in hydrogen sulfide. To modern animals, such waters would be hostile. To certain microbes, they were home. This reminds us that habitability is not one fixed thing. A world that seems poisonous to us may be perfectly ordinary to life adapted to it. In this slow, layered sea, oxygen did not simply make the world better. It made the world different. It closed old pathways and opened new ones. It pushed some organisms away and invited others forward. The planet did not become modern, but it became less like its earlier self. A threshold had been crossed. From far away, Proterozoic Earth might still look quiet. Clouds pass over oceans. Low continents stand bare under the sky. No forests darken the land. No animals disturb the seafloor. But inside the air and water, the chemistry is moving toward a future that will eventually allow larger cells, greater energy use, and the long road to complex life. For now, the transformation remains soft and slow. Oxygen gathers, then pauses. Methanephades, then shifts with volcanic input. Iron disappears from the water and settles into stone. Microbial mats keep working in the shallows. The sky above them is beginning to change. And so the camera rises again, past the oxygen bubbles, past the rusty particles falling like red dust through the sea, up toward the surface where ancient light trembles. Above the water, the air is no longer exactly what it was. The haze is thinning. The chemistry is rearranging. The sky, which once belonged to methane and volcanic breath, is preparing to become clearer, bluer, and more protective, one molecule at a time. The sky above Proterozoic Earth did not begin as the gentle blue ceiling we know. It was a changing sky, a chemical sky, a sky still learning its own colors. If you could stand safely on a bare shoreline and look upward, you might not see the familiar, soft blue of a modern afternoon. You might see a thicker haze, a warmer tint, a sky touched by orange or brown, depending on the gases drifting through the air. There would be no birds crossing it, no leaves moving beneath it, no distant mountains softened by forests. Only rock, water, cloud, and light. The planet would feel open and unfinished, like a stage before the actors arrive. Although the smallest actors were already everywhere in the water. Before oxygen became common, methane helped shape the atmosphere. It trapped heat and may also have formed hazes when exposed to sunlight. These hazes could scatter light in unusual ways, giving the sky a dim, smoky quality. Scientists believe that early Earth may sometimes have resembled a world under a permanent dusty sunset, not because dust filled the air, but because organic particles formed from methane chemistry. It is strange to imagine a sky that was not blue. We tend to treat blue as the default, as if Earth was always waiting with the same clear dome above it. But sky color is not a promise. It is chemistry meeting sunlight. It depends on gases, particles, pressure, and the way light scatters through air. Change the air, and the sky changes with it. As oxygen began to accumulate, it reacted with methane. Methane declined. The old haze thinned. The atmosphere slowly cleared. There was no single morning when the sky switched from brown to blue. No sudden curtain lifting. Instead, over immense spawns of time, the old filters faded. More sunlight scattered through a changing atmosphere. Blue wavelengths became more visible. The world began, very gradually, to take on a more familiar light. Imagine a long sequence of dawns. At first, the horizon glows through a thick amber haze. The land below is bare and muted. Low waves fold against a shore of stone. Millions of years pass. The haze is less dense. Shadows sharpen. The water reflects more cleanly. Millions more. The sky is still not modern, not stable, but it has changed. The light has opened. Oxygen did something else, high above the surface. When ultraviolet light from the sun struck oxygen molecules, some of them split and recombined to form ozone. Ozone is made of 3 oxygen atoms. Near the ground it can be harmful, but high in the atmosphere it becomes protective. It absorbs much of the ultraviolet radiation that once reached Earth's surface without much resistance. Before this protective layer formed, the surface was difficult for fragile life. Ultraviolet radiation could break apart organic molecules and damage cells. Water gave protection, which is one reason life remained mostly below the surface. But with ozone slowly forming, shallow environments became safer. Not safe in a modern sense. Not yet welcoming to plants or animals. But less harsh. A little more open. A little more possible. The atmosphere was not only changing in color, it was changing in function. It was becoming a shield. You might picture sunlight entering the upper air. Invisible ultraviolet rays strike oxygen molecules. The molecules split, recombine, form ozone, and gather in a faint high layer. It is not visible from the ground. No creature looks up and thanks it. There are no eyes, no lungs, no skin exposed to the breeze. Yet this thin chemical shield will become one of the reasons complex life can eventually move toward the surface. The ground below also began to record oxygen. On Barlan, iron in sediments and soils reacted with the new gas. Red beds formed, oxidized rocks stained by iron. These rocks are signs that oxygen had reached the atmosphere in meaningful amounts. They are like quiet red signatures written across ancient landscapes. The land, once chemically different, was beginning to rust in the open air. Picture rain falling on a barren Proterozoic plain. There is no grass to soften it, no roots to hold soil, no insects beneath stones. The water moves across rock, carrying minerals, reacting with exposed surfaces. Oxygen in the air touches iron in the sediment. Over time, red layers form. A color enters the land that could only appear because the atmosphere had changed. This was not a steady climb toward modern oxygen. The Proterozoic atmosphere moved in pulses. Oxygen rose, stalled, dipped, and rose again. For long intervals, levels may have remained far below what animals would later need. Enough to alter minerals. Enough to create ozone. Enough to change microbial environments. But not enough for large active bodies. The planet had taken a step, then entered a long pause. Scientists sometimes call a large stretch of the middle Proterozoic the boring billion. It is a gently unfair name, and perhaps a little rude to a billion years that did its best. The phrase refers to a long period of relative geochemical and evolutionary stability. When oxygen levels remained low, continents shifted slowly, and visible life did not change dramatically. But boring depends on where you stand. If you are waiting for animals, it seems quiet. If you are a microbe adjusting to a layered ocean, it is home. During this long middle time, the carbon cycle worked like a slow planetary thermostat. Volcanoes released carbon dioxide. Rain reacted with rocks on land. Weathering carried dissolved materials to the sea. Carbon became buried in sediments. When more carbon dioxide remained in the atmosphere, Earth warmed. When more was removed, Earth cooled. Tectonics, weathering, oceans, and microbes were all part of the same slow exchange. Methane no longer dominated as it once had. Oxygen had made methane less stable in the air. Carbon dioxide became more important for long-term climate balance. The atmosphere was less hazy, but also more vulnerable to cooling when greenhouse gases declined. This mattered deeply during later glaciations, when ice would spread across the planet and reflect sunlight back to space. Sulfur and nitrogen also moved through the system. Volcanic gases released sulfur compounds. Microbes used sulfur in their metabolisms. Some environments became rich in sulfide. Nitrogen, abundant in the atmosphere, had to be fixed into usable forms by life. Microbes capable of nitrogen fixation helped make this essential element available to ecosystems. Their work influenced productivity, carbon burial, and oxygen production. Again, the smallest organisms touched the largest systems. The atmosphere became a place of cycles. Gas from volcanoes entered the air. Rain carried chemicals to rock. Rivers moved minerals toward oceans. Microbes transformed them. Sediments buried them. Tectonics eventually lifted or recycled them. The same elements moved through air, water, stone, and cell, again and again, in loops so slow that only rock can remember them. All this happened beneath a sky that no one saw. There were no animals to watch the first clearer sunsets, no eyes to see sharper shadows on bare stone, no one to notice that the high atmosphere had become more protective. The world changed without witnesses. This is one of the quietest truths of deep time. For most of Earth history, beauty happened with no observer, except, perhaps, the planet itself. If we allow ourselves that gentle thought, down in the shallow seas, microbial mats continued their steady work. Stromatolites rose, layer by layer. Cyanobacteria caught sunlight. Other microbes lived below them, where oxygen faded. The atmosphere above them responded to their chemistry, and they responded in turn to the atmosphere. More oxygen changed the surface. Less methane altered climate. Ozone softened radiation. Every layer of the planet was speaking to the others. Though the conversation took millions of years per sentence, the changing sky also changed light in the water. As haze thinned and sunlight became clearer, shallow environments received different qualities of radiation. Ultraviolet decreased under ozone protection. Visible light could penetrate in altered ways, depending on water clarity and atmosphere. Microbes that relied on light adjusted to these conditions. Life did not need eyes to respond to the sky. Molecules were enough. A cell can feel light without seeing. In this long, calm interval, Earth appears almost still from a human perspective. Continents drift too slowly to notice. Oxygen remains low. Microbial life continues. But beneath the stillness, preparation is underway. The atmosphere is gaining structure. The surface is becoming less hostile. The oceans are developing more complex chemical layers. And inside the microbial world, cells are beginning to change in ways that will matter later. The Proterozoic is full of this kind of quiet preparation. A sky clears before there are eyes. Ozone forms before there is life on land to depend on it. Oxygen rises before animals exist to breathe it. Continents stabilize before forests need soil. It is like watching a room being arranged for guests who will not arrive for hundreds of millions of years. There is something peaceful in that. The planet is not rushing to produce anything. It is simply changing. Light meets gas. Rain meets stone. Cells meet chemistry. Time passes. 1 billion years can feel empty only if we forget how much can happen slowly. Let the image linger. A wide, bare continent under a changing sky. Low clouds moving across rock. Red sediment staining a quiet basin. Far away, a shallow sea catches the morning light. Its surface is still. Beneath it, microbial mats breathe oxygen into the water. Above it, high in the atmosphere, ozone forms and breaks and forms again. No animal watches. No wing crosses the air. Yet the stage is becoming gentler. The sky is no longer only a barrier or a hazard. It is beginning to become protection. The land is no longer chemically sealed from oxygen. It is beginning to weather in new ways. The ocean is no longer purely old and anoxic at the surface. It is becoming layered, restless in chemistry, ready to support new possibilities. And so, from this changing sky, the view returns slowly to the shallow seas. The water is calmer now. The light is clearer than it once was. Across the seafloor, microbial mats spread in thin living sheets. Their surfaces shine faintly under the sun. They are small, but they are organized. They are soft, but they build stone. In the next part of the journey, we will stay with them, close to the mud and the light, and watch how life made cities long before it made bodies. The view settles low over a shallow coast, where the sea is calm enough for sunlight to reach the bottom. There are no shells here, no fish, no waving plants, no shadow of a swimming animal passing over the sand. The surface of the water moves gently, and beneath it lies one of the most successful worlds Earth has ever made. At first glance, it does not look like much. A dark green film on mud, a soft brown layer across stone, a low rounded mound in the shallows. If you were walking there, safely and impossibly, you might be tempted to step past it. The way people sometimes ignore a quiet person in a room until later they learn that person was holding the entire conversation together. These are microbial mats, thin living carpets built by bacteria and archaea, layered by light, chemistry, and patience. They are not simple in the way they appear simple. They are small, yes. They are soft, yes. But inside them, life is arranged with surprising care. At the top, where sunlight is strongest, cyanobacteria gather light and use it to make food. They split water. They release oxygen. They create sugars that feed their own tiny bodies. Just beneath them, where light is weaker and oxygen begins to fade, other microbes wait for the leftovers. They use waste products, process sulfur, recycle nutrients, and keep the whole layered community moving. Deeper still, in darker and more oxygen-poor zones, different cells work with slower chemistry, breaking down organic matter and returning it to the layers above. A microbial mat is only a few millimeters or centimeters thick, but it behaves like a landscape. Light at the top, shadow below, oxygen near the surface, anoxic conditions deeper down, nutrients moving upward and downward, waste becoming food. A whole world compressed into mud. This is why it can help to think of them as tiny cities. Not cities with streets or windows, of course, but cities of function. There is energy production. There is recycling. There is chemical communication. There are neighborhoods, each one suited to a narrow set of conditions. No mayor is required, which, for a microbial city, may be a relief. Everything is organized by gradients, by what is available, by what each kind of cell can do. Over time, some of these mats trapped sediment. A tide would bring fine grains of sand and silt. The sticky surface of the mat would hold them. The microbes would grow upward again, covering the new layer. Then another tide, another dusting of sediment. another upward growth. Minerals formed. Layers hardened. Slowly, the mat became a stromatolite. A stromatolite is a collaboration between life and stone. It grows so slowly that watching one would test even the patience of a mountain. Yet, over thousands of years, low domes and columns could form across shallow seafloors. Some were small and rounded. Some were broad and flat. Some rose in clustered forms, like a quiet garden built from sediment and time. Imagine the camera moving just above them. The water is clear enough for sunlight to ripple across their surfaces. Their tops are soft with living film. Their sides are layered. Tiny bubbles rise from places where photosynthesis is active. A thin wave passes over them and bends the light. Then the tide returns. A little sediment settles. Another layer begins. For much of the Proterozoic, stromatolites were among the most visible signs of life on the planet. Visible is a generous word, because they still looked like rounded rocks to any eye that might have existed. But there were no animals to graze them down, no snails scraping the surface, no fish disturbing the sediment, no worms burrowing through the mats. The microbial world could spread and hold its place. This long microbial reign lasted not for a few million years, but for vast stretches of time. That is one of the hardest things to feel. Human history is so brief that even a few thousand years can feel ancient. The Proterozoic asks us to imagine hundreds of millions of years when the main drama of life unfolded in films. Layers, chemical exchanges, and slow growth. Nothing hunted in the familiar sense. Nothing fled. Nothing watched. There were no eyes, no mouths, no teeth, no skeletons, no fiends. Life was busy, but not theatrical. It was a planet of processes. Absorb, convert, release, divide, drift, attach, sense light, follow chemicals, wait. And yet, this world was not passive. Microbes communicated through chemical signals. A cell could respond to light without seeing it. It could move toward a nutrient or away from a harmful condition. Some microbes used flagella, tiny whip-like structures, to swim through water. Others clung to surfaces. Others floated with currents. Some formed colonies. Some exchanged genes directly, a process called horizontal gene transfer, which allowed useful traits to move between lineages. Evolution was already clever long before brains existed. That is a comforting thought in a quiet way. Life did not need a mind to explore possibility. It only needed variation, time, and an environment full of chances. The fossil record of microbes is difficult. Tiny soft cells do not preserve easily. They decay, dissolve, or leave only faint traces. But the rocks remember in other ways. Stromatolite layers preserve the architecture of microbial communities. Chemical signatures show patterns of photosynthesis, sulfur metabolism, methane production, and nitrogen cycling. Certain molecules point to particular kinds of organisms. Isotopes record who was using carbon, who was changing the chemistry, who was quietly shaping the sea. The result is a picture of a world crowded with life, even though almost none of it had form we would recognize. A world where the living surface of a mat could be more biologically active than a bare continent. A world where the most powerful organisms were too small to see. Down in the deeper ocean, far from the shallow stromatolite fields, the story continued in darker tones. Sediments rested in stillness. Chemical gradients formed through mud. Hydrothermal vents released heat and minerals. Microbes near vents used chemical energy rather than sunlight. Others lived buried in the seafloor, their metabolism so slow that time around them seemed almost still. Some may have divided rarely, waiting through long intervals of scarcity. They were not dramatic survivors. They were patient survivors. That kind of patience was one of the great strengths of microbial life. A large animal needs much: food, space, oxygen, movement, repair. A microbe can live on thin margins. A little chemical energy, a surface, a pocket of moisture, a narrow band where one condition meets another. The Proterozoic rewarded that skill. It is tempting to treat this era as a waiting room before the interesting life appears. But that would be unfair. The microbial world was complete on its own terms. It had producers, recyclers, chemical specialists, cooperation, competition, adaptation, and resilience. It did not know that animals would come later. It did not need animals to justify itself. Modern life still rests on this microbial foundation. Microbes cycle nitrogen in soil. They help digest food in animal bodies. They live in oceans, rocks, clouds, hot springs, ether, and deep beneath the surface. They still run much of the planet from behind the scenes. We tend to notice the large things: trees, whales, birds, ourselves. But the small things keep the systems working. In the Proterozoic, that truth was even clearer. The entire biosphere was microbial. The ocean surface, the sediment, the vents, the mats, the air chemistry, all of it was linked to the activity of cells. If the planet had a pulse, it was microbial. The camera lingers over a stromatolite field as the ancient day passes. Morning light spreads across the water. At noon, the surface brightens. The mats produce oxygen. By evening, shadows lengthen over low domes. Night comes, and different chemistry takes over. The top layers rest from sunlight. Lower layers continue to process what the day produced. The community shifts, not with thought, but with chemistry. Then dawn returns, and the slow cycle begins again. This rhythm continued for ages. Layers grew. Sediments hardened. Some stromatolites were buried and preserved. Others were eroded, broken, recycled into younger rock. Continents drifted. Atmospheres shifted. Ice would later come and go. Yet microbial mats remained one of the great stable forms of life. And within this small world, something new began to stir. Not a creature with limbs. Not an animal. Not even a multicellular body. A shell, but a different kind of cell. Larger, more internally organized, carrying its DNA in a more protected place, filled with compartments that could divide work inside a single living boundary. The eukaryotic cell did not arrive like a sunrise that suddenly lights the whole sea. It appeared quietly, probably gradually, among microbial communities still dominated by bacteria and archaea. But its arrival mattered, because a cell with internal structure could do new things. It could become larger. It could manage more information. It could form partnerships inside itself. It could become the ancestor of plants, animals, fungi, and so much more. For now, the microbial mats continue their soft labor in the shallows. The stromatolites grow another thin layer. The water glows under late light. And somewhere in that invisible world, life begins to turn inward, building complexity not yet in bodies, but inside the cell itself. Think of that inward turn as a quiet change in architecture. The outside world remains almost the same. Water moves over mats. Sediment settles. Light fades and returns. But inside certain cells, space begins to be organized differently. A boundary forms around genetic material. Internal scaffolding guides movement. Tiny compartments begin to manage tasks. It is not yet a body, but it is no longer only a simple room. It is becoming a house with chambers. No one could see it. No fossil would capture the exact moment, but the consequences would travel forward for the rest of life. The same seas that held stromatolites also held the first hints of a future in which cells would no longer only live beside one another. They would carry ancient partnerships within themselves. The view moves closer now, past the surface of the mat, past the films and grains, past the tiny bubbles and chemical layers, until the world becomes cellular. At this scale, the Proterozoic feels less like an ocean and more like a universe of membranes. Each cell is a small boundary, a little inside, separated from a vast outside, holding chemistry together against the pull of the surrounding sea. For more than 1 billion years, most life had been built from simple cells. Bacteria and archaea are wonderfully successful that way. They are efficient, adaptable, and able to live almost anywhere. Their DNA is not sealed inside a nucleus. Their internal structure is relatively simple. They do not need much. And because they do not need much, they have survived nearly every change Earth has offered. But during the Proterozoic, a different kind of cell began to appear. There was no bright flash in the water, no visible boundary where the old world ended and the new one began. It emerged quietly, gradually, probably through many steps that scientists are still trying to understand. This was the eukaryotic cell. A eukaryotic cell is larger and more internally organized than a bacterium. It has a nucleus, a protected compartment where DNA is stored. It has internal membranes. It has structures that help move materials from one place to another. It has a cytoskeleton, a kind of inner framework that gives shape and movement. It is not just a bag of reactions. It is a small, organized world. If you could drift inside one, gently and impossibly, it might feel like entering a harbor at night. There are boundaries channels, signals, and a central archive protected behind a membrane. The cell is still microscopic, but its internal life is richer. It can manage more information. It can grow larger. It can begin to do several things at once. One of the most important events in this story was symbiosis. That word means living together. It sounds peaceful, and sometimes it is, though in early evolution it may have begun in ways less polite. One cell likely took in another. Perhaps the smaller cell was intended as food. Perhaps it was already living nearby in a mutually useful way. Scientists continue to study the details. But at some point, a bacterium ended up inside another cell, and instead of being digested, it stayed. That bacterial partner became the ancestor of mitochondria. Mitochondria are often called the powerhouses of the cell, a phrase many people remember from school, sometimes with the exhausted expression of someone who also remembers an exam. But the phrase is useful. Mitochondria help cells produce energy efficiently, especially using oxygen. In a world where oxygen was becoming more common, that ability mattered. The original mitochondrial ancestor was probably a free-living bacterium capable of using oxygen to release energy from food. Inside the host cell, it offered a powerful advantage. It could produce large amounts of ATP, the small energy-carrying molecule that cells use for work. In return, the host offered shelter and raw materials. Over time, the relationship became permanent. This did not happen in a single afternoon. The partnership stabilized across millions of years. Genes moved from the bacterial partner into the host nucleus. The former bacterium lost much of its independence. The host became dependent too. Eventually, neither side was truly separate. The mitochondrion became an organelle, a working part of the eukaryotic cell. Even now, mitochondria carry traces of that deep past. They have their own DNA. They divide in ways that resemble bacteria. They have double membranes. They are like tiny fossils living inside modern cells. Not fossils made of stone, but living memories of an ancient merger. Every animal, plant, fungus, and many other eukaryotes carry this inheritance. The importance of that merger is difficult to overstate. More energy allowed cells to become larger and more complex. A larger genome could be maintained. Internal compartments could be built and powered. The cell could afford complexity in a way simpler cells often could not. Some eukaryotes later formed another partnership, when a photosynthetic cyanobacterium became the ancestor of chloroplasts. These structures still allow plants and algae to capture sunlight. Once again, evolution did not only compete, it incorporated. There is a quiet lesson there. Although we do not need to make it too sentimental, life often advances through cooperation as well as competition. The most important step is not always to defeat another organism. Sometimes it is to live together so completely that after enough time, the partnership becomes identity. The early eukaryotes were still small. They were not animals. They did not have nerves, tissues, or organs. But they were different from what had come before. Some could engulf other cells, bringing food inside themselves. This opened the door to predation at the cellular level. Life was no longer only absorbing dissolved chemicals. Some cells were beginning to eat other cells. That changed the rules. If some cells could engulf, other cells benefited from defenses. They might grow larger, form coverings, become more mobile, or stay in groups. Interactions became more spatial. Position mattered. Movement mattered. Detection mattered. The world of life was still microscopic, but it was becoming more dynamic. Eukaryotic cells also carried more internal regulation. With a nucleus and more DNA, they could develop complex control systems. Genes could be turned on and off in more elaborate ways. Cell shape could change. Movement could be guided by internal scaffolding. The cell could respond to its environment with more flexibility. The fossil evidence for early eukaryotes is subtle. Some microfossils are larger than typical bacteria. Some show complex walls or internal organization. Chemical markers and molecular evidence point back into the Proterozoic. None of these clues is as clear as a dinosaur bone, but together they form a quiet pattern. Complex cells were here. Then came another innovation, one that seems ordinary now because nearly all complex life depends on it. Sexual reproduction. For a long time, life reproduced mostly by division. One cell became two. Two became four. This is efficient, simple, and still extremely successful. But it produces copies, with variation mainly through mutation. Sexual reproduction does something different. It mixes genetic material from two sources, shuffling DNA into new combinations. The process is slower and more complicated, which is very on brand for nature when it decides to improve something. But the result is powerful. Variation increases. The earliest forms of sex were likely simple compared with what we know today. Cells may have fused briefly, exchanged genetic material, then separated or divided. Over time, more structured processes evolved. Meiosis reduced chromosome number. Gametes formed. Fusion restored the full set of genes in new combinations. The details would become many and varied across different lineages, but the basic effect was the same. Offspring were not exact copies. They were new mixtures. This mattered greatly in a changing world. Oxygen levels shifted. Oceans changed chemistry. Ice ages came and went. Continents drifted. Environments were not steady forever. Populations with more genetic variation could adapt more readily. Harmful mutations could be separated from helpful ones. Useful combinations could appear more often. Sex gave evolution more material to work with. At this stage, there were no flowers, no mating dances, no songs, no antlers, no elaborate rituals. Those would come much later. The earliest sexual processes were cellular and quiet, hidden in water. Two tiny living systems meeting, merging, exchanging, dividing. Still, in that small exchange, the future widened. Sex also required recognition. Cells had to find compatible partners or states. They had to signal, respond, synchronize. These simple interactions helped set the stage for later cooperation. A cell that can recognize another cell has begun one of the long paths toward multicellular life. And that path began to appear too. Some cells divided and did not fully separate. They remained attached in clusters, chain, sheets, or small colonies. At first, this may have been accidental, but staying together can offer advantages. A group may be harder to engulf. Cells can share resources. Some can specialize slightly, doing one task while neighbors do another. Over time, a cluster can become more than a cluster. It can become a body. Multicellularity did not evolve only once. It appeared in several lineages, including algae, fungi, animals, and other groups. The early steps were simple. A chain of cells, a hollow sphere, a flat sheet, a colony with slight division of labor. But even simplicity can be revolutionary when it changes what selection can act upon. Evolution could begin shaping not only individual cells, but groups of cells working together. To do this, cells needed communication. They needed signals to control growth, position, and function. They needed ways to prevent cheating, because in a cooperative body, one cell growing without restraint can harm the whole. The beginnings of regulation, development, and cellular discipline were part of the long preparation for complex life. It is helpful to remember that all of this happened slowly. The first eukaryotes did not instantly become animals. The first sexual cells did not instantly produce complex ecosystems. The first multicellular clusters did not instantly swim or crawl. The Proterozoic was not rushing toward a finish line. It was expanding the range of possible life. In the water, microbial mats still spread. Stromatolites still grew. Bacteria and archaea still dominated by numbers, diversity, and metabolic reach. Eukaryotes were newcomers, probably scattered and rare at first. But they carried new architecture. They carried mitochondria. Some lineages carried chloroplasts. They carried larger genomes, internal compartments, genetic mixing, and the first hints of bodies made from cooperating cells. The camera pulls back slightly. We see an ancient shallow sea under a softened sky. Nothing appears dramatic at the surface. A mat glistens. Sediment drifts. The water is quiet. But inside that quiet, life has learned a profound new idea. A cell can contain another cell. A genome can mix with another genome. A divided cell can stay with its neighbor. Cooperation is no longer only a microbial mat. It is becoming internal, genetic, and bodily. The world is still small, still almost entirely invisible, still far from animals. Yet the foundation is changing. Complexity has entered the story, not as a creature, but as a possibility. And ahead, the planet will test that possibility with ice, deep cold, drifting continents, and long intervals of endurance. The world grows colder now, but the change begins almost too slowly to feel. At first, ice gathers where cold already belongs. High latitudes brighten under pale sunlight. Glaciers thicken. Snow lasts longer from one season into the next. Then the white begins to spread, reflecting more light back into space, cooling the planet further, inviting still more ice to form. This is the beginning of one of the strangest chapters in Earth history. During the later Proterozoic, Earth may have entered periods of extreme global glaciation, often called snowball Earth. Scientists continue to debate how complete the ice cover was. Some models imagine a planet sealed almost from pole to equator. Others suggest a slushier world, with open water in places, cracks, thin ice, and dark refuges where life could continue near the surface. But either way, the evidence points to cold on an enormous scale. From space, the planet might have looked pale and quiet, more like a frozen moon than the living blue world we know. Continents lay under ice. Oceans may have been covered by thick sheets, perhaps hundreds of meters deep in places. Winds moved across a bright surface with little to stop them. Sunlight struck the ice and bounced away. The old seas, once dark and chemical, became hidden under a lid of white. The evidence for these ancient freezes is found in rocks. Dropstones, large stones carried by ice and released into fine marine sediments. Glacial striations, scratches carved by moving ice across bedrock. Glacial deposits in places that were once near the equator. These clues are calm in the field, just stone resting in stone. Yet they point toward a planet passing through severe cold. What caused such a freeze? There was probably no single cause. The sun was still dimmer than it is today. Methane had declined as oxygen rose, weakening an important greenhouse blanket. Carbon dioxide may have been drawn down by weathering, especially when fresh rocks were exposed by tectonic activity. Once ice began spreading, the ice itself made the problem stronger. White surfaces reflect sunlight. More reflection means less warmth. Less warmth means more ice. This is called a feedback loop. It is not dramatic in a human sense, but it is powerful. A little cooling becomes more cooling. A little ice becomes more ice. The planet drifts toward a state that is hard to escape. Imagine standing above an ancient ocean, if standing were possible, and seeing ice stretch to the horizon. No waves, no blue surface, just a pale, wind-marked plain, with dim sunlight sliding across it. Under that ice, the ocean remains dark and liquid. It still moves. It still holds salts, minerals, and living cells. Earth is frozen at the surface, but not dead. Life survived by using the quiet places. Deep below the ice, hydrothermal vents continued to release heat and mineral-rich fluids from the seafloor. Around those vents, microbes could live without sunlight, using chemical energy from hydrogen sulfide, methane, and other compounds. These communities had already learned to ignore the mood of the sky. Whether the surface was bright, hot, frozen, or dark, the vents kept breathing. In shallower settings, life may have survived beneath thinner ice. In cracks, brine channels, meltwater pools, or small openings called polynias. Wind, geothermal heat, and ocean circulation might have kept patches of water from freezing completely. In these narrow refuges, photosynthetic microbes could still receive enough light to endure. Not flourish, perhaps. Not spread widely, but remain. There may also have been life inside rocks, under the surface of land, or within sediments. Some microbes can slow their metabolism to almost nothing. They can wait. They can persist on tiny amounts of energy, protected from radiation, buffered from cold, hidden from the worst of the world above. This is not heroic survival in the way humans like to imagine it. It is quieter than that. It is the survival of patience. A microbe does not need courage. It needs a tolerable chemical corner. The cold likely lasted for millions of years. To say that gently is almost absurd. Millions of years of ice. Millions of years of dim light reflected away. Millions of years with life pressed into refuges, reduced, slowed, and hidden. Yet the planet beneath the ice remained active. Volcanoes continued to erupt. Carbon dioxide continued to enter the atmosphere. Normally, weathering removes some of that carbon dioxide, as rain reacts with rock and carries dissolved material to the sea. But when much of the planet is frozen, weathering slows. Carbon dioxide can build up. Slowly, the greenhouse effect strengthens. The air traps more warmth. The ice begins to lose its certainty, perhaps first near volcanic regions, perhaps at low latitudes, perhaps in dark patches where dust or meltwater absorbs more sunlight. Cracks widen. Meltwater runs. Ice shelves break. The white planet begins to open. The thaw would not have been perfectly gentle. When a frozen world warms, stored changes arrive quickly by geological standards. Glaciers melt. Seas open. Weathering returns with force. Rivers carry fresh minerals into oceans. Carbon dioxide reacts with newly exposed rock. Nutrients surge into shallow waters. Microbes bloom. Oxygen rises again in places. The world that emerges from ice is unstable, but rich with opportunity. For life, the thaw is not just relief. It is renewal. Refuges connect again. Isolated populations expand. Nutrients that had been locked away pour into the seas. Photosynthetic organisms regain sunlight. Eukaryotes that survived in hidden pockets find broader habitats. Some of the oldest evidence for more organized multicellular life appears after these great glaciations. Scientists do not say that ice directly created complexity, but it may have cleared space, changed chemistry, and opened new paths. The camera now pulls away from ice and looks deeper, toward the continents themselves. While life endured cold and chemistry, the ground beneath the ocean and ice never stopped moving. Plates drifted across the planet, carried by heat from the mantle. Continents assembled, broke apart, and assembled again. This long, tectonic movement shaped climate as surely as the air did. One early Proterozoic supercontinent is often called Columbia, or Nuna. Its exact shape is uncertain, because the evidence is old and scattered. But matching rocks, mountain belts, and magnetic clues suggest that pieces of what are now North America, Baltica, Siberia, and other regions once lay joined. Later, another great supercontinent formed, Rodinia, around 1.1 billion years ago. Rodinia was vast, and its assembly raised mountains, altered ocean basins, and changed how wind and water moved across Earth. A supercontinent is not only a map, it is a climate machine. When land gathers into one huge mass, rainfall patterns change. Interior regions can become dry. Coastlines shift. Ocean circulation reorganizes. Mountains rise where continents collide, then slowly erode, sending minerals into rivers and seas. Those nutrients feed microbes and later more complex life. The shape of the land changes the chemistry of the ocean, and the chemistry of the ocean changes what life can do. Rodinia also eventually broke apart. Heat built beneath the thick landmass. Rifts opened. Magma rose. New ocean basins began. Fragments drifted away from one another with the slow grace of stone rafts. The breakup may have influenced later snowball Earth events by changing weathering rates, volcanic output, and ocean circulation. It may also have helped create more shallow marine habitats when the climate recovered. This is how the Proterozoic works. Nothing acts alone. Microbes alter gases. Gases alter climate. Ice alters weathering. Volcanoes alter air. Continents alter oceans. Oceans alter life. Every system speaks to every other system, but very slowly, in a language of rock, water, wind, and time. The atmosphere, during this later span, remains in motion too. Oxygen does not rise in one smooth climb. It pulses, stalls, and rises again. For much of the middle Proterozoic, oxygen stays low compared with modern levels. Enough to change minerals and support some new metabolisms, but not enough for large, active animals. Then, later, oxygen begins to increase again, especially near the end of the eon. The stage becomes more generous. The carbon cycle continues its long breathing. Volcanoes release carbon dioxide. Rain weathers rock. Rivers carry ions to the sea. Carbon is buried in sediments. Tectonics lifts and recycles. The atmosphere is not separate from Earth. It is one part of a great, slow machine, connected to mountain roots and microbial mats, to ice sheets and ocean basins. It can be calming to see Earth this way, not as a fixed object, but as a set of rhythms, freezing and thawing, assembly and breakup, burial and uplift, oxygen rising and falling, life shrinking into refuges, then spreading again. A planet does not sleep like an animal, but it does have long cycles of quiet and change. By the end of this part of the journey, Earth has been tested by cold, reshaped by moving continents, and refreshed by thawing seas. Life remains mostly small, but it has endured. Eukaryotic cells have survived. Some cells are beginning to live together more persistently. Oxygen is becoming more available. New ecological spaces are opening in the shallow oceans. The frozen world softens. The continents drift under a clearing sky. Rivers return to bare land. Minerals wash into seas where microbial mats still glow under sunlight. And in those waters, cells begin to do something simple and profound. They stay together, not just as neighbors but as parts of a larger living form. At first, these forms are modest. A chain, a sheet, a small cluster held together after division. Yet, in deep time, modest beginnings matter. A body does not have to arrive fully formed. It can begin as a few cells remaining close, sharing signals, discovering that togetherness can be another way to survive. In the newly opened seas after the great freezes, life begins to look a little different. Not suddenly, not with a burst of movement or color. The world is still quiet, still mostly microbial, still ruled by chemistry and smallness. But some cells no longer live only as solitary units. They remain together after division. They form filaments, clusters, sheets, and small, organized bodies. Multicellularity is beginning to take hold. At first, this may seem like a small change. One cell divides, and the two daughters do not drift apart. They stay attached. Then another division, and another. A chain forms, or a hollow sphere, or a thin sheet. But staying together opens a new kind of possibility. Cells can begin to share work. Some may handle feeding. Others may help with movement. Others may become better suited for reproduction. A group can become more than a crowd. This did not happen only once. Multicellularity appears to have evolved many times in different branches of life. Algae, fungi, slime molds, plants, and animals each explored versions of the same idea. The first attempts were simple, and many remained simple. But even a simple cluster changes what evolution can shape. Natural selection can begin to act not only on a single cell, but on the arrangement of many cells. To stay together, cells needed communication. They needed signals. They needed ways to decide when to grow, when to divide, where to remain, and what role to take. They needed enough cooperation to prevent one cell from taking over at the expense of the whole. In the smallest possible way, early bodies had to develop rules. This sounds almost social, although there were no thoughts involved. No cell sat down and decided to be considerate. Chemical systems did the work. Genes turned on and off. Molecules moved from cell to cell. Gradients formed. A body plan, even a very simple one, is a kind of agreement written in chemistry. Oxygen helped. Mitochondria helped. More energy made larger and more complex cells possible. Rising oxygen allowed metabolism to support bigger structures. Predation may have helped too. A cluster of cells can be harder to engulf than a single cell. Grouping together may have been protection before it became architecture. In the late Proterozoic, especially after the last major snowball Earth events, the fossil record begins to show larger and more organized forms. This later interval is called the Ediacaran period. It lasted from about 635 million years ago to about 541 million years ago. It is the final chapter of the Proterozoic, and it feels like the first soft light before a very different dawn. The Ediacaran world was still not modern. The oceans held more oxygen than before, but likely far less than today. Microbial mats still covered large areas of seafloor. Continents were shifting. Nutrients washed into the oceans after glaciations. The chemistry was changing. Life had more room to experiment. And then, in the rocks, we begin to see shapes. Not bones, not shells, not teeth. Soft impressions in ancient sandstone. Quilted bodies pressed into sediment. Fronts, discs, ovals, ridged forms. Strange leaf-like shapes resting on the seafloor. Some organisms may have lain flat on microbial mats. Others may have stood upright in the water, anchored gently to the bottom. Some reached sizes that would have seemed enormous compared with earlier microscopic life, even up to a meter in length. It is hard to know what many of them were. Some scientists believe certain Ediacaran organisms were early animals. Others may belong to extinct branches of life with no close modern relatives. Some might have been colonies. Some may have absorbed nutrients directly through their surfaces, rather than eating with a mouth. Many had no obvious head, no limbs, no organs that we can identify with confidence. They are familiar enough to feel alive, and strange enough to remain mysterious. Imagine an Ediacaran seafloor under soft filtered light. The water is calm. The sediment below is covered in microbial mat, a thin, living carpet. Across it rest broad, quilted forms. A frond sways gently in the current. A disc-shaped organism lies partly embedded in the surface. Nothing rushes. There are no fast predators, no schools of fish, no reef noise. It is a quiet garden of soft bodies and ancient experiments. Some fossils show evidence of movement. Simple trackways wind across old seafloors, suggesting that certain organisms could reposition themselves. These are not dramatic trails of pursuit or escape. They are slow marks, perhaps left by an organism gliding, creeping, or feeding along a mat. Still, they matter. Movement changes ecology. Once life can move with purpose, place becomes a choice. The Ediacaran organisms lived in a world where microbial mats were still central. The mats may have provided food, stability, or a surface to live on. Some organisms may have grazed gently. Others may have absorbed dissolved organic matter from the surrounding water. We do not know every detail. The fossils are impressions, not complete bodies. They are like pressed leaves from a forest that no longer exists. Except the forest was on the seafloor and did not have leaves. Their preservation is remarkable because soft bodies usually vanish. Without shells or bones, most living tissues decay quickly. But microbial mats helped. They stabilized sediment and may have sealed impressions before they disappeared. In this way, the ancient microbial world helped preserve the first larger forms that began to rise from it. The old world kept the memory of the new. Then, near the end of the Proterozoic, these forms begin to fade. Around 541 million years ago, the fossil record changes. Burrows become more common. Tracks become more complex. Hard parts begin to appear. Animals with clearer body plans enter the story. The Cambrian period begins, and with it comes a more dynamic biosphere. Movement, feeding, defense, shells, eyes, and ecological interaction increase. The Ediacaran organisms did not necessarily vanish in one dramatic ending. Some may have left descendants. Some may have been outcompeted. Some may have belonged to experiments that simply did not continue. Their disappearance is still debated, but their importance remains. They show that multicellular life had become visible before the Cambrian. They are the soft threshold between a microbial Earth and an animal Earth. The Proterozoic itself ends quietly. There is no single day when the planet changes eons. No bell rings across the ocean. Boundaries in geology are drawn by scientists looking at rocks, fossils, chemistry, and time. Nature does not pause for our labels. The transition into the Phanerozoic, the eon of visible life, was gradual. Still, something real had shifted. Earth was ready for a new pace. By the end of the Proterozoic, oxygen had risen enough to support larger metabolisms. Eukaryotic cells had emerged. Mitochondria had made energy use more powerful. Sexual reproduction had increased variation. Multicellularity had appeared in several lineages. Continents had grown and shifted. Snowball Earth had tested survival and renewal. The oceans had changed from iron-rich and anoxic toward more layered and oxygenated environments. Everything needed for the next great expansion of life was in place. The Cambrian explosion, when it came, did not come from nowhere. It was built on Proterozoic foundations. Every animal with muscles, nerves, symmetry, and a body plan depended on groundwork laid during this long, quiet eon. Oxygen, energy, cooperation, genetic mixing, cellular architecture, environmental change. All of it had been prepared in the slow rooms of deep time. And the Proterozoic is not only behind us, it is inside us. Every breath you take depends on oxygen made possible by ancient photosynthetic microbes. Every cell in your body depends on mitochondria, descendants of bacteria that entered into partnership more than 1 billion years ago. Your DNA carries molecular systems with roots in ancient cellular life. The membranes, energy pathways, genetic code, and reproductive machinery of modern organisms all reach back into that quiet world. You are not separate from deep time. You are a continuation of it. The microbial world did not disappear when animals arrived. It remains the foundation. Microbes live in soils, oceans, hot springs, clouds, rocks, and bodies. They help digest food, cycle nutrients, make vitamins, and regulate ecosystems. By number, diversity, and reach, they still rule much of Earth. The age of microbes never truly ended. It simply gained company. Imagine the final view. A Proterozoic sea near the end of the eon. Microbial mats still cover the seafloor. Soft ediacaran forms rest in gentle water. Above them, the sky is clearer than it once was. The continents are shifting. Oxygen moves through the air. In the sediment, faint tracks mark the beginning of a more active world. Nothing roars. Nothing flies. But the future is close. The camera rises slowly from the seafloor, through calm water, past suspended particles, toward the surface. The ocean reflects the pale sky. From space, Earth looks quiet and blue, but now it carries new possibilities. The long preparation is nearly complete. The Proterozoic did not end because it had failed. It ended because it had done enough. It built the air, shaped the seas, strengthened the continents, refined the cell, taught life cooperation, and opened the door to bodies. It gave Earth the slow foundation on which visible life could stand. The world you know is young compared with that long preparation. Forests are young. Animals are young. Human voices are almost new. But beneath all of them, the Proterozoic remains. In oxygen, in stone, in cells, in the deep memory of life. Rest now with that old earth beneath you. The wind over bare rock has faded. The frozen oceans have opened. The microbial mats are still beneath the shallow water, breathing slowly in sunlight. The first soft bodies rest on the seafloor, and beyond them, the future waits without hurry. Good night.